The broadcast is now starting. All attendees are in listen-only mode.
Hi everyone, this is Carrie with Test Oil. Thank you for joining our webinar today. Evan and I have our webcams on so you can see us. We get comments all the time that, during webinars are so boring because you can't see the people. Well, you'll be able to see us just in the beginning, but then when Evan goes ahead and starts the training session, we'll be turning our webcams off. Just a couple of things to let you know, just to get started. First, how about, let's see, can everybody hear me? If you can hear me, can you click on the little paw or the little hand in the GoToMeeting? There you go. I see some people that are clicking on there, so y'all can hear me. Okay, great. So during the course of the webinar, we are actually going to keep everybody on mute. If you're familiar with the way that we run these, I record them so I can send them to you later. A lot of people use these for training for the rest of their staff. It's nice to watch it later. And if I don't have the audio shut off, we can get a lot of background noise that just makes it not a very nice recording. Also, a couple things to notice in the toolbar. There is a handout section towards the mid-bottom. There is an ebook that you can download. It's on sampling best practices, which is perfect for what our webinar is about today. And also throughout the course of this webinar, we're going to ask a couple poll questions. So be ready to interact with us. Make your best bet at answering our questions, and then Evan will make sure that you get the right answer. So with that, see some people asking some questions. I'm going to go ahead and start. I'm Carrie Williams. I'm the Director of Training. I've been with Test Oil for about 10 years. I've been doing our webinars for a good portion of that. I really love the ability to, kind of talk with our customers and interact in this way. And we have Evan, who is our Senior Technical Advisor. He's our lead instructor. He goes out to our customer locations and does on-site training. He also does all of our on-site audits for our customers. Evan also does certification training, and so we are the team that you would talk to if you're interested in doing any of that. So with that, I'm going to go ahead and turn off my webcam. I'll let Evan do his presentation, and I'll jump in a couple times here and there with the poll questions.
All right, sounds good. Okay, so today's presentation is on sampling best practices, and essentially I've broken it out into 5 sections. So what we're going to first talk about is understanding why it's so important to take good samples, and then I'll walk you through some of the tools that are available to help take better samples, which will lead us to a discussion on if and where we should sample certain machines, and then decide to install these tools to help with the sample taking procedures. Once we've covered that, I will describe in brief what it takes to pull a good sample, so a little bit on the procedures, and then I'll wrap up with a discussion on the frequency. So we'll sort of get the why, the how, the where, and then of course the how often. Now, one of the things I always say about oil analysis is if I was to summarize oil analysis into one single sentence to describe what it is, I would say oil analysis is all about establishing what's normal and simply waiting for it to be not normal. When you look at other condition monitoring tools like thermography, vibration, ultrasonics, most of these technologies have been developed to the point where they have clear identifiable patterns, thresholds, alarm limits, whatever you want to consider them to be, where you know when there's a problem. Oil analysis does not have this luxury necessarily. It relies a lot more on the trend than it does on any static values. So without taking good samples, it's hard to see that trend because you tend to add too much noise to the trend. And that noise leads to missing potential problems that you could have caught, which of course is unscheduled downtime, or sometimes the noise appears like problems and then you chase your tail trying to fix things that aren't really there to be fixed. So when I talk about normal, what I mean by normal is if you can take consistent samples, you will figure out what normal looks like for any one machine. And by consistent, I mean consistent location, procedure, and frequency. And it's really the frequency is one of the things that a lot of people don't realize how much of a difference that can make. But we'll talk about that as we go through the presentation. And what we're ultimately trying to do is decide how can we take a representative sample. And when you ask people to define representative sample, it's very difficult to do that without using the word representative in the definition. And ultimately, what I use to describe a representative sample is I say it's a sample taken that clearly shows you what you're looking for, meaning like, are you looking for degradation? Are you looking for wear? Are you looking for contamination? Are you looking for effectiveness of your filtration system, or whatever it is? But the sample's taken in such a way it can clearly show you that. So it's representative of the area of concern, but also it's taken in such a way that represents the true conditions, right? If you take a sample and simply open up that valve and take the first stuff that comes out, that's not necessarily what all the circulating oil looks like. So it's not just where you take the sample, it's also how you take the sample. So that's what we'll discuss in some greater length here. Now, ultimately, when you think about taking samples, if you're going to take bad samples, I say it's better not to sample at all then. Because if you're taking such bad samples that you add way too much noise to the data, you're really not going to have an effective oil analysis program. Now, obviously, sampling properly is going to be better than not taking samples, but what I stress is sampling from a good location is one thing, but sampling from a great location, even if you don't have the best of procedures, is better yet. Really, the location matters a lot more and is one of the harder things to change. So if we can get the location right, we get better data, but we can always work on the procedure later. But there's no point having an excellent procedure if the location is lousy. So let me give you an example here of a hypothetical system. Imagine any system that's got some kind of reservoir that is equipped with a drain, and also somewhere within the system, doesn't have to be on the reservoir, there are filters. So the two samples I'm going to describe to you are these. Sample number one is a sample that you would go to that low point drain, bottom of the reservoir, you'd knock that valve open and let it drain for 10 full seconds, and then capture the next 4 ounces that comes out. There's your sample number one. Now sample number two, you're going to go to wherever the filters are located. You're going to go to the upstream side of the filters, the dirty side, the inlet side of the filters, and you're going to open up the vent, valve, plug, port, whatever happens to be there, and collect absolutely the first 4 ounces that comes out, meaning no flushing whatsoever. So there's our first poll question to you, is which of those two samples do you suppose is the better sample, the one more representative of all the fluid within the system? We'll give you a few seconds to answer here. Well, it seems like the trending answer is that sample number one is the better sample. And think about this for a second though. If you take a very well flushed sample from the drain, what are you going to see? You're going to see what the bottom of your reservoir looks like, which is probably not your greatest concern. Reservoirs are meant to be garbage pits. They're meant to be where the fluid collects all of its large debris, water, stuff like this. So that's not a great sample to have. That doesn't tell you very useful data about all the oil in the system. Sample number two actually is the better answer. So for the 38% of you that picked that answer, good for you. That did get the right answer in terms of which one was better at showing you all the fluid within the system, because it is live circulating fluid if it's flowing through the filters. Now, the point is, sample number one has a great procedure, but a lousy location. Sample number two has a great location, but a lousy procedure. So what if we can combine both of those? So ultimately, what we're trying as a goal here is to sample with the right procedure from a great location, and this is going to give us the best data possible in the best manner. Now, as I always say, sometimes you have to be practical though. Sometimes the best location isn't one that's easy to access or isn't one that's easy to get oil out of, or just offers a great deal of difficulties in obtaining that samples. And you do balance this with practicality, but where it makes sense, right, we take the samples and we make sure we have a good procedure, and we get good data, and therefore we have an idea of what normal looks like, and that's ultimately our goal. Now, the next section's a bit on sampling tools here. So these are all real-life examples of bottles that have come through to our lab.
Evan, I can go ahead and jump in and talk about these if you have a second.
Sure.
Okay, so I thought these were funny to add to our presentation, and they're actually, I guess, not funny, because these are some of the actual samples we've received in our lab. So I'm going to kind of go through and talk about each one of them. The first one right there in the top in the middle, that, if you can tell, is a coffee cup. So I think it's like a styrofoam coffee cup, and someone actually took the time to figure out a way to wrap that up with some cellophane and seal it, tape it up. I don't know how they shipped it to us without it spilling over, but you know, that can't be too contaminant free. The next one, if you go kind of to your left counterclockwise, I know we've received samples in Coke bottles, Pepsi bottles, water bottles, anything you can think of that's got a lid on it. People think it's an appropriate something to send a sample in. The ones in the bottom middle kind of make me laugh. That's a little jelly jar. And I know Evan always tells the joke, it's the gift that keeps on giving from the Jelly of the Month Club. And then the little Estee Lauder makeup jar. So someone actually went home and, you know, found these containers and decided it was a good idea to fill them up with a sample. And then the next one is the Fiji water. So much like the other water bottles to the left of it, you know, the lubricant in there is quite milky, which would make you think that there's water in there, right? But so how do we know? Was there water? Is there actually water in the equipment where the sample was pulled from, or is there water left over from when they dumped out their water bottle and decided to fill it up with the oil? And then the last one is the Gatorade bottle, and this is kind of a good example of why all of these are dangerous to use. So if you look at this list, these are all of the ingredients that are on the label of a Gatorade bottle. And the ones in red are things that could come up on an oil analysis report. But the danger here is, if you look at the last two that are in red, if we received an engine oil sample and these showed up as being in that fluid, that would maybe make us think that there could be coolant in there. So these are two items that could show up as coolant in a lubricant. Did I cover that right, Evan?
Yep, no, that's very much the point here, that yeah, using a proper sampling container will give us good data. Using any of these things is likely to lead us on a stray path. So assuming then we've got a proper sample bottle to take samples in, what I'd like to go through is a quick short list of common tools that we use to get the oil into those sample bottles in a what I consider to be convenient, safe, above all, consistent or repeatable fashion that hopefully are much less prone to contamination, so that you're not adding things in, like Carrie was saying there, that show up on the report and make us think that's in the system, when really it's just something that got in the bottle. So most of these tools I'm going to show you are variations on a sampling valve. They're all rated for higher pressures, some of them upwards of 9,000 psi. So there's probably no system out there that you can show me where we can't find a tool that would help take a sample from there and reduce the pressure to safe levels. Almost all of them have size and thread options to them. So whether they're NPT, SAE, left hand, you know, Japanese metric, whatever it happens to be, you can probably find them that will thread directly in, or with maybe one bushing, be able to be retrofitted into an existing system using existing plugs or ports. Most of these are also equipped with some kind of dust caps on them to keep them sealed, so that when they're not in use, they're not getting dirty and requiring a lot of effort to clean them up before you take a sample. And most of them are inexpensive and small enough that you can probably install them in secondary locations that you can use at times when you're trying to really pinpoint which component is failing or which part of the system is experiencing the problems. So first and foremost, one of the more common ones that exists out there is the mini mesh style. These ones are just little thread-in adapters. They have a thread-on dust cap, seals with an O-ring, so the valve stays perfectly clean when it's not in use. It does require an adapter to open the valve, so whether this is a push-in style adapter or a thread-on adapter if you're wanting to control the flow or the pressure a bit more. But they're a very versatile tool, come in a number of different sizes. There's the regular flow, like I'm showing you here. There's a higher flow version if you're dealing with thicker oils or just have systems that have maybe very low or non-existent pressure. One of the more common ones that I recommend tends to be that same style of valve, but with a pitot tube as well. This enables you to reach deeper into the system and get closer to that live area, that area where the oil is actually moving, circulating, and away from the edges of the casing or a reservoir, or even to be able to sample from above the fluid level, right? If you're going to use maybe a fill cap, a breather plug, or even a top-up overflow style plug, you can reach in with a pitot tube and bend it in such a way that you can get towards that live circulating oil. Now, one of the other ones that I commonly recommend is this version of a sight glass adapter. Basically, you can take a sight glass and upgrade it to a 3D sight glass, so that right away gives you just a better sight glass. But this one also has a sampling valve installed right through it, because if there's one thing you know about a sight glass, it's that there's oil behind it. So this allows you to sample directly from that oil, but again, with a pitot tube that reaches in so that you're not sampling the stagnant oil near the sight glass, and it's bent downwards so that you are ensuring it's always in the oil level. Now, for some folks, one of the only openings into a system that's got line of sight to the oil is the drain, right? Sometimes the fill caps, breathers, and all that, you can't stick tubing in there. You couldn't stick a pitot in there and hit the oil, but there is always, of course, oil behind the drain. This one retrofits an existing drain with a pitot tube up through the center. Off to the right in this picture, your drain still exists, and often you can equip that with a quick connect so that you can use a pump to actually suck the oil out and maybe do your oil changes a little bit faster. Optionally, on the left, you can add a level gauge, so if you didn't already have one, now's a way of adding one in, and you can now have an easy way to confirm the level in the system's okay. But pretty much all of those are the more common ones that I do recommend when I'm out there auditing, and they generally can make taking samples go much faster with more repeatability, consistency, and of course a lot less contamination. Now, even when I recommend these type of pieces of hardware, the one thing I would never say is that you can't simply get away with a quarter turn ball valve. Right? That's as much of a valve as you need to sample any oil from any system. As long as you can open it, you can get oil out of it. Now, you may actually have to use a vacuum pump to suck it out. You may have pressure enough that it comes out on its own, but it works. It doesn't have to be complicated. Just generally when people install things like these type of ball valves, they also have a length of piping or tubing to connect the ball valve. And it should be understood that everything from that ball valve back towards the live circulating oil, you'd have to flush all that oil out. So it's not that you can't get away with this type of valve, but it does require more flushing. Generally on the output of this valve, it's a pretty good idea to install something to prevent contamination. Now, some people lean towards putting a plug in the end, which is great the first time it's used, but plugs have a tendency to go missing. So a lot of people just put a 1/4" 90 on it, whether it's made out of stainless steel tubing or it's just they purchase an elbow kind of thing. But at least they install one of those and point it downwards, and that helps prevent normal airborne contamination from building up excessively on the outside of that valve. It's not perfect, but it does work, and it can be made to work if it's treated properly.
Evan, is this a good time?
Any of these systems, you will need, if there's no or low pressure, a way of pulling it out. So we do have suction pumps to be able to do this.
Evan, can we go ahead and throw a poll question in real quick?
Sure. Now, thinking about these vacuum pumps here, does anybody have a good idea as to how do you stop the flow in a vacuum pump. What's the fastest way of doing this? So we've put up a poll there and see if you have an idea of what makes the most sense for stopping the flow using a vacuum pump. Well, I'm glad to see the first two answers trended very low. That's good. To stop the flow of oil using a vacuum pump, you must first understand the operation of a vacuum pump. It's quite simple. On the bottom of the pump, you screw the bottle to it, and it seals against an O-ring. Through the top of the pump, you insert the tubing, and there's an O-ring at the top of the pump as well that seals the tubing. Now, once you've got that all sealed, by drawing on the pump, basically it's like a backwards working bicycle pump, you create a vacuum inside the bottle. So if you want to stop the flow, the one thing that's not going to work very well is pulling the tubing out. If you pull the tubing out of the sample point, you still have a vacuum existing within the bottle. So all that means is you stop the flow of oil into the tubing, but still your entire tube will have to empty into the bottle. So it doesn't really slow down the flow initially. Now, if you try and crimp the tubing like a garden hose, what you probably find is that actually doesn't work very well. The tubing's stiff enough that, generally speaking, that doesn't work for most folks. But the best way to do it is to simply break the vacuum and the flow will stop. And the two choices that trended, more people chose to unscrew the top than unscrew the bottle. My favorite is to unscrew the bottle because it takes about a quarter of the turn on the bottle and the vacuum is broken. I also have good leverage on the bottle, and I'm going to unscrew the bottle eventually anyways, so that's my preferred method of stopping the flow. It's not to say that unscrewing the top doesn't work, but I do find it takes more twists of the ferrule to get that open, and ultimately, I don't need to unscrew that first anyways. I want to get the bottle off so I can get the cap on the bottle first, then I'll unscrew the top of the pump and pull the tubing out because, as you're going to see in the next slide, we recommend that you replace the tubing with every sample. So, like I said, I'm glad to see most people do not pick the first two answers because those are not terribly effective. Where breaking the vacuum is definitely the better way to go. If you look at the example in the picture there, it actually has a separate valve just for doing that. So if you can get those style pumps, of course, then you just press the valve and away you go. But one other point I'd like to make about these vacuum pumps while we've got the slide up here is that when it comes to using these, I find most people have a fairly good idea how to set it up and get the oil flowing into the pump. But there's a couple small, quick little tips I'd like to give to make sure that the pump works as well as possible for as long as possible. And mainly that's about inserting the tubing. When you insert the tubing, a lot of people stop the tubing when it hits the bottom of the pump. I'd like to encourage you to stick it in about a half an inch past that so the tubing reaches all the way into the bottle. Now, I know anybody with experience is going to say, hey, the oil's going to get into the bottle either way, but my point is that the tubing goes past the pump as the oil comes out of the tubing. If it splatters in any kind of way, is not likely to contaminate the pump. Also, if you cut the tubing at an angle rather than a blunt cut, the oil as it comes out of that tubing, when it's at a slow flow, it will not spatter as much, and it will form nice smooth droplets, again, just preventing the pump from getting contaminated with oil. Now, those two tips aren't much, but I'm just trying to keep the pump clean, because if I get the pump dirty, if it in any way gets oil on it, I have to clean the pump before I take the next sample. Otherwise, I risk cross-contamination. So those two tips are just there to help make sure that your sample taking doesn't involve any unnecessary extra steps. But the tubing, as I said, generally speaking, when you take a sample, you should replace that tubing each and every time. It is so inexpensive, it really does not make much sense to try and recycle it. The stuff's worth about 10 cents a foot. So the second you try and spray brake clean through it or any other solvents, you've probably spent more on the solvent than you have on the tubing. And then you have to factor in the labor involved and everything. So one of the things I always like to point out, just to make sure everyone's aware of how we do things at Test Oil, is that if you are our customer and you log into our website, you can click order supplies, and you can order sample bottles, vacuum pumps, and tubing. And they're all free. We don't charge for any of that because these should not be hurdles that people have when they take samples. But about the tubing, if you actually schedule your oil samples through our website, give us an idea how often you're taking your samples, we will send out your supplies in advance. So we'll provide you with the bottles, but not only that, we'll pre-print your labels and give you a length of tubing. So you will have tubing each and every time you take samples. So again, it kind of eliminates that excuse of, you know, I'm trying to save it. Right? You should always have plenty of tubing on hand. It's so inexpensive, there's no reason not to. But saying that about the tools, let's talk about the if and where we should sample. So the first question being if. It's always a good question to ask yourself, does it make sense to sample it? So these are the 6 criteria that I try and use to decide if it's worth sampling. And ultimately, these 6 criteria, basically, if you can meet any one of them, it's worth sampling. But if you can't meet 1 out of 6 of these criteria, you really have to take a look at it and say, maybe I just don't sample it and I focus my efforts elsewhere. So number 1 is criticality. If you can say a piece of equipment is critical, meaning if it shuts down or ceases to operate at its full capacity, you suffer downtime or maybe reduced output or efficiency, or if its failure cascades and causes other things to failure, all these things essentially define criticality. So if it's critical, it's worth sampling. What about safety? And what I mean by that isn't that if it fails, is there a chance somebody gets hurt? Because that argument can be made for a lot of things in life. But more what I mean is it a piece of equipment designed to encourage or enhance safety? Like, is it your fire water suppression system? Is it the emergency braking system on an elevator? Is it a backstop on a conveyor? These are the kinds of things that in theory, you actually never expect to run. But if you need them, you want to make sure they run. So those kinds of things, well, they're worth sampling. Now, if it's expensive, and by expense, I mean downtime, parts, labor, anything. If it costs your company a lot of money when this thing doesn't work as well as it should or stops operating, then again, it's probably worth taking some oil samples. Reliability is another factor. And what I mean by reliability is I mean sort of unpredictable reliability, right? If you buy pumps or gearboxes or some other small component, and you've been told that it'll last 8,000 hours, and you get 1 year's worth of service out of it every time you buy them, well, that's actually fairly reliable for what you need. But if you buy things rated for 20,000 hours, and some of them fail after 5,000 or 12,000 hours, and you have no way of knowing this, well, oil analysis may help define what's occurring before it goes into that failure mode, and therefore, it's worth sampling. Efficiency is another one not a lot of people consider, but again, if something's not operating at its usual efficiency, not necessarily meaning high efficiency, but at its usual efficiency, if you start noticing higher energy consumption or less output or anything like that, maybe some more data would help identify why that is. So again, it could be worth sampling. And last but not least is the environment. If that piece of equipment is operating in a harsh environment, meaning it's at a high temperature, it's at a high humidity, there's a lot of particulate in the air, things like this, then there's a greater chance that oil is going to become contaminated, and that's one of the #1 killers in any system is contamination. So again, it becomes worth sampling. So once we've decided it's worth sampling, we need to decide then where to sample it. And the ideal location in any system is actually dependent on another question. And that is, what do you want to know? And what you want to know seems like a pretty intuitive answer, but really you could be asking different things than somebody else who's performing oil analysis. Because ultimately what you're wanting to know is something that's helping achieve a goal. And the 4 most common goals that I know why people do oil analysis are listed here. Some people are simply trying to reduce how much oil they're using, because oil may be a significant cost, or at least the PM tasks related to changing the oil cause enough downtime or enough other related costs that this is a significant savings if they can simply extend their drain intervals. Other people know that they operate in harsher environments with a lot of particulate or moisture, and as long as they can keep the oils clean, they can run them as long as the OEM recommends, and they're happy that way, and they have fewer failures. So some people are looking to monitor their contamination. Other folks usually have something like mean time between failures or some other acronym they love to use. And basically, we just want our equipment to last longer or require fewer parts changes or rebuilds. So we'll monitor the wear that's occurring to determine that. And last but not least, everyone's favorite is increase uptime. Right? More people are looking at the overall availability or the uptime of their machines, and so they're looking to make sure that they can get as much of that as possible. The point of these 4 different goals is that I can arguably get the answer to each of those 4 questions or 4 goals from 4 different sample points, and I may not actually be able to answer all 4 questions from each of those sample points. So let me give you an example. Here's a very typical lube system. This is what is delivering lubricant to another machine. What the other machine is not important to our discussion, but you can see it has a reservoir, it has onboard filtration, and it has some pumps. Now, if you take a look at those pumps and you say, well, those pumps are critical. If the pump fails, we're not delivering lubricant. Therefore, whatever the machine is, we could fail it. We could cause it to trip. Something could go wrong. Well, then your sample point location becomes those pump outlets, because you want to verify that the pumps are in good operation and they're not shedding wear material and all those kinds of things. So that becomes your primary sample point. Now, if you look at this picture and say, but wait a minute, there's 2 pumps. If one fails, the other one can pick up the slack. Therefore, it's not critical. Well, I can't disagree with that. But maybe you want to monitor how clean the oil is that's being delivered to the machine. Well, then you'll sample from the pump outlet, or perhaps the pump inlet, or sorry, the filter inlet and outlet. You want to confirm that the oil going out of the filters is clean and being delivered to the machine in whatever target cleanliness you're going for. Now, if you look at this and say, but wait a minute, we already said the pumps were duplicated, therefore they're not critical. If you look at those filters and say, well, they've got a differential pressure switch or a gauge on them, and therefore you can confirm that the filters are functioning without needing an oil sample. Well, again, I can't argue against that, and you need some other data. Well, what if you want to change the oil based on condition? Well, then your sample point location becomes somewhere out of the reservoir. And really, at this point, it actually doesn't matter too much where in the reservoir you take it, top or bottom. You will get your answer as to the condition of the oil. Now, again, if you take one last look at this and go, pumps are duplicated, they're not critical, filters have a differential pressure gauge on them, don't need a sample from there either, and you change the oil on schedule, time-based oil changes, so you don't need to know necessarily the condition of the fluid. Ultimately, your only concern is that machine that we're lubricating. Well, then your sample point becomes the return line to the system. Right? That is the best sample point to answer that question. So as you can see, it really matters what you're trying to figure out in terms of where you're going to take that sample. Now, speaking from a common perspective, most people concern themselves with the machine that's being lubricated and would pick that return line. But that doesn't mean it's right for everybody. I said, if you had any of the other concerns along the way, you would pick one of the other sample points. So consider this. Some tests are affected by the sample point location, and some tests are not really affected by the sample point location. So our next poll question for you is, what kind of tests do you think are affected by that location? So we've opened up a new poll for you here, and let's see how we answer this question. All right, you seem to be picking a lot of the right answers here. So ultimately, the best way to answer this question is to think, is it contamination or wear related? Because if it's contamination or wear related, then yes, it will be affected. So whether we're talking about the wear metals or the contaminant elements, if we're talking about particle counting, water content, any ferrous debris, or even the sort of gamut of all of those put together that you might get out of analytical ferrography, definitely affected by location. Right? If you took a sample from before a filter compared to after a filter, the sample from after the filter would potentially show less wear particles, lower particle count, less ferrous wear, and certainly that would affect the analytical ferrography. Now, water content could be affected by something as simple as before or after a reservoir, because water, again, may settle out in those areas. But the kind of tests that are not affected are anything to do with the physical and chemical properties of the lubricants. So whether we're talking about just the viscosity, if we're talking about acid and base numbers, definitely not affected by location. If we're talking about engine samples, then the fuel content tends to dissolve and dilute into the oil, so it doesn't really matter where that is. Glycol tends to dissolve in fairly well, or at least form an emulsion, so it doesn't separate that readily. And then your soot levels are held in place by the dispersants. So even though those are kind of wear and contamination related, in engine oils, they're not generally going to be affected by the location. So ultimately, we need to be aware of this when we pick a location, because if we pick an area that is not going to have some of this stuff show up, and that's what we're really trying to find out more on, well, then we've just affected our results by picking a poor location. So kind of the long and the short of what you're looking for is you want an area with turbulent flow. You want live circulating oil. That's going to give you generally the best representation of what's going on. So on or after elbows, downstream of work areas, on return lines, inside that reservoir, any of the area that's agitated, all those are good areas to get live flow. But ultimately, you want any of those to be upstream of any filters, to the point that you can actually go right up until the inlet side of that filter, and it's still considered a good sample. Now, depending on the application, you may be stuck with a dipstick as one of your only ways into the system that gets you a line of sight to the oil. That can work. And as a last resort, while you're draining the oil out, you can simply catch a midstream sample just to make sure it's as representative as possible. What we're trying to avoid, though, is the sampling from dead legs, which would require a significant amount of flushing to make those valid. Sampling out of sight glasses directly, because again, the oil in a sight glass may be very stagnant. And without proper flushing, we tend to avoid drains. That usually requires a lot more effort, creates a bit of a mess, and again, probably only gives us a really good view of what the bottom of the reservoir looks like, not necessarily what the live circulating oil is. So if the system's big enough, it becomes a definite no. So now we need to decide, once we have a location identified, maybe we've retrofitted it with one of those sample valves I showed you, maybe we just have a quarter turn ball valve, or maybe just a plug. How do you actually take the sample from there? So some of the key criteria you look for is that you want to make sure that it is an easy task. You want to make sure that it is safe, convenient, and repeatable, because if it's not one of those three things, well, then it's not likely to be done the same way every time. So what I look for is ways to try and make sure that we can keep it that way while still getting ourselves a representative sample. So we try and avoid certain things. Like, we don't like to sample when things are shut down. Now, if they are shut down, we try and get there within that first half hour, because then the oil's still hot and everything should be still suspended. But if it's been shut for a while, we're probably not getting the live oil anymore. If we don't clean the area around where we're sampling, there's a good chance stuff's going to get inside that bottle that's not really within the system, and we're going to contaminate the sample. It's going to lead to our data suggesting the problem exists when it really doesn't exist. And above all, if we don't flush, we'll never get a real live view. So these are all common mistakes that we're seeking to avoid. So ultimately, I've tried to whittle this down into as short of a discussion as possible, because taking a sample properly is actually pretty easy. So here's the 5 steps I think it comes down to. Basically, there are 5 single words you have to remember. Step 1, wipe it. Wipe the area around the sample. I don't mean make it absolutely clean. You don't have to go to that extent when you're wiping it. What I mean is you're wiping the area around where you're sampling, whatever that plug port valve happens to be, and you're getting it clean enough so that when you hold the bottle underneath wherever that valve is, or you're connecting your tubing, or whatever it is you're doing to extract the oil, nothing's going to end up in the bottle that isn't just the oil from the system, right? No chunks are falling off and landing in the bottle. You're not in any way brushing material in, that kind of stuff. So step one, wipe. Step two, flush. You want to flush enough oil from whatever that plug port valve happens to be until you get live representative oil. Well, a lot of people have asked, how much oil should I flush? Right? Sometimes you read 3 times the volume, 5 times the volume, 6 times the volume. And now let's go, what volume? How do you estimate a volume between the outside of that valve and all the little tubing or piping or whatever all the way back to the system? It's difficult sometimes to estimate that and then do a projection of what 5 times or 6 times that volume might look like. So my point is, flush it until it comes out hot. Once that oil is coming out hot, you know you've got live oil. So flush at least until it comes out hot. You can flush more. There's no harm in that. And certainly, the more the merrier, but at some point you're not getting any effect on that. So you're just wasting oil. But at least flush the sample port, flush the tubing that you're using. And if you're going to take the time to flush that, you might as well rinse it through the bottle just to make sure the bottle doesn't have any contaminants that may have entered the bottle since you opened it. And it's a way to contain the mess. Now, once you've got things flushed, fill the bottle. So filling the bottle, we ask that you don't fill the bottle much above about 3/4, 80% full, because we need some headspace in that bottle. And the headspace isn't there for shipping. It's not like we expect the sample to expand. If anything, it's actually going to contract, because usually you take the sample when it's hot, and of course it cools down during shipping. So it's not about shipping that we really need that headspace. It's really about what's the first step the lab does when they get your sample, and that is they shake it. So if you fill the bottle right full and we shake it, well, nothing happens. We don't really mix it back up. So if you leave some headspace, when we shake it, we can mix it all back up and make what's in the bottle representative again. Now, once you've got the bottle at the right fill level, next step, cap it. No sense leaving it open and allowing contamination to enter the bottle because you just left it open. Right? Cap it immediately. And in the capping, of course, one of the things we're looking for, if it has not already yet been done, label it. Right? Our customers are shipped out pre-printed labels that they can slap on the bottle before they even open the bottle. But if you're not having these labels in the field, well, at least have a Sharpie on you and write on the cap whatever the machine number is or an identifier, so that you don't mix up the samples. Because, of course, when most people take samples, they take more than one sample, and you don't want to mix these up. So cap it as soon as you've got it full, and therefore you're not allowing any contamination to get in. And the final step is quite simple. Send it in. Right? There's no point sitting on a sample. Some people have said they wait till they fill the box back up. Some people sit there and wait until a complete lube route has been completed after several days. No, send the samples in as quick as you can, as quick as is practical. Right? There's no point sitting on them. Our turnaround time is same day. So we're not the reason your results take a long time. Generally, shipping is. And shipping, most places ship to us overnight shipping. We have a special deal with UPS to pick samples up first thing in the morning before the trucks even head out. So we get that part of it covered as quickly as we can in terms of receiving your samples and processing them through the lab within, like I said, the same day. So take the time to do your end of it and send them in within a day or two of sampling. Right? Maximum 48 hours is kind of the goal to make sure your oil analysis program wraps up in a fashion that allows you to get the data soon enough to react to it and not have problems that showed up in oil analysis trigger a failure. So like I said, it comes down to these 5 words.
Hey, Evan.
Flush, fill, cap, and send.
I'm sorry, Evan, could you real quick just share your analogy about folding a paper airplane? I thought that was such a clever thing that you came up with in that article that you wrote in TLT magazine, and I think everyone can relate to it when you talk about it in the sense of folding the airplane.
Sure. Yeah, ultimately, when I was asked about doing some training on site to teach people how to take samples, I said that it wasn't really necessary because taking a sample is actually a pretty simple task. And the analogy was it's as simple as folding a paper airplane. That ultimately, in about 5 steps, I can tell you how to fold a paper airplane. I can tell you to take a piece of paper lengthwise and crease it. That's step one. Step two, fold the top corners down. Step three, fold the corners down again. Step four, fold the wings back over. So once it's folded together, now fold it in the other direction. And step five, undo it to extend, like fold it back out, so you've got yourself a little airplane. Now, in those 5 steps, anybody could follow those and create a paper airplane. But if we all did this and we all threw the paper airplane, well, some of them would fly straight, probably not that many. Some would hang left and some would hang right and some would just shoot for the floor. And you go, okay, well, it wasn't a hard task. It was simple, right? Folding a paper airplane is not complicated, but why did it not work? Well, if we all tried a second time to fold a paper airplane, and we paid really good attention to how crisp those folds were, would that make a difference? Well, maybe it would, maybe it wouldn't. But if we tried a third time, after learning how to make the folds nice and tight, but if we tried a third time and tried to make the folds symmetrical, well, now we're starting to get somewhere. And the analogy was simply that a simple task is not easily done. A simple task simply means there's not a lot of steps to it. But the ease in which it's done is also how easy it is to make a mistake or not get a step just quite right. So the whole folding a paper airplane analogy was to illustrate it's very simple to fold a paper airplane, but it's hard to get one to fly far and straight. But what gets you there, of course, is practice. And if you were to fold 10 paper airplanes in a row, and by the time you got to that 10th paper airplane, it'd probably be a pretty decent one. It probably would fly a little further, a little straighter, and you'd be happy with it. So ultimately, following these 5 steps of wipe, flush, fill, cap, and send, a little bit of practice goes a long way. And, that's what's going to get you better. You don't necessarily need to see somebody else do it to know what to do right. You just need to practice it and take care at each step. And again, they're simple, but simple doesn't always mean easy. Easy to do is also, like I said, easy to make mistakes. Yeah, there's the analogy. Now, just so we have it within the context of our presentation, I did include sort of the side steps involved with taking samples 4 different ways. So I've included a slide here on how to take samples from a properly installed sampling valve, how to take a sample if you're taking it from below the fluid level, from above the fluid level, or if you're last resort, have to take samples out of a drain. But ultimately, they're basically reiterating those same 5 steps. So our last section here is now the frequency. You decide if it's worth sampling, where you're going to sample it, and how you're going to sample it. The last thing you have to figure out now is how often you're going to sample it. And why this comes into effect is, like I said at the beginning, if you want to develop an idea of what normal looks like, you need to take consistent samples. That's a consistent location, which is easy to do if you install a valve that says all samples taken from here. A consistent procedure, which again might be easy if you keep it real simple. But the last step is a consistent frequency. And what I mean by this is if you decide on quarterly sampling, which ultimately means every 90 days, but for whatever reason, you let it slide for a few days and it develops into a couple of weeks and it ends up being not 90 days, but almost a month late. It's 120 days later. Well, if you take that sample at 120 days rather than 90 days, it's probably not that big of a deal. But what happens when you take the next sample and you try and get back on track? Well, if you get back on track, that next sample occurs after 60 days, because that's now the next scheduled time you should have taken a sample had you been taking samples every 90 days. So the problem is that you have one sample at 120 days worth of oil service, and you have another sample now at 60 additional days of oil service. There's a 100% difference in the service intervals on those. So when we start taking samples like that, we cause variations in how much the data should be trending. So that adds a lot of noise to the data. Now, if we don't take samples often enough, there's a potential that we miss stuff. If we take them too frequently, we might just overload ourselves. We call it analysis paralysis, when you start taking way too many samples and you can't get through the reports. Or you just don't even see the changes anymore because they're so close to each other, you just can't see the overall trend. So you fall into complacency that way. But that irregularity is one of the worst. And that's probably the more common issue that I find, is people have an idea of what that schedule should be, but they don't really adhere to it that strictly. So how do we establish what that interval should even be? Well, two methods that people use are related to the PF curves. What some people do is they go to 1/2 the PF interval, half the time between a potential failure and the time it takes to develop into a functional failure. And that kind of logic actually plays not bad when it comes to ultrasonics, thermography, and vibration. It really works against you when you apply it to oil analysis. It tends not to be quite often enough, and you don't tend to see the trends, and you sort of miss most of the common failures. So the other theory, which gives you way more data, is to start shortening the interval, increasing the frequency as you get closer and closer from P towards that F, towards that functional failure. And this logic, again, plays out even better than the first logic when it comes to vibration, thermography, and ultrasonics, but really, really works against you when it comes to oil analysis. It has what I consider to be flawed logic. So let me show you what I mean by that. Here is a table giving exactly the same data twice, but in the first column on the right, I'm going to assume a normal trend. On the column to the far right, I'm going to assume that trend is abnormal, and let's see what the data should or would tell us. So in the first column, the data goes from 5 parts per million to 9 parts per million. That's a change of 4 parts per million. The next, it changes from 9 to 15, so that's a change of 6 parts per million. Well, on average, a change of 4 and 6 work out to be an average of 5. So if I wait one full interval before I sample that system again, it would stand to reason that the next piece of data at sample number 4 should look like approximately 20 parts per million. But if I decide to sample at a half interval, to sample slightly more frequently, if I sample at interval 3.5, what should that piece of data look like? And well, the number halfway between 15 and 20 is 17.5. So that would be what the data would show, assuming that's a normal trend. But what if it's not a normal trend? Well, if the data changes from 5 to 9, which is a difference of 4, and then changes from 9 to 15, which is a difference of 6, if that trend was to continue, then the next piece of data should be at least 8 parts per million higher. So the data at sample number 4 would probably look something more like 23. Now, if you were to sample at a half interval, what would that piece of data look like? Now, before we too quickly answer halfway between 15 and 23, which would be 19, understand this is now an exponential curve, and therefore it'd be a little bit lower than the halfway point. So it would probably look more like 18.5. Now, my point of walking ourselves through this exercise is if you wait a normal interval from sample 1, 2, and 3, and wait till it reaches the interval where you take sample number 4, well, you're trying to decipher the difference between a value of approximately 20 and a value of approximately 23. I think that's a pretty obvious difference, and you could confirm if the trend was normal or not normal. But if you were to take a mid-interval sample, shorten the interval by half, right? Take the sample twice as often now. We're trying to decipher the difference between 17.5 and 18.5. And to be fair, spectrometric data, like the kind that is reported in parts per million, doesn't tend to be reported with a decimal place. So those values would likely be rounded. So it's quite possible that 17.5, of course, would round up to 18, but that 18.5, if it was 18.49, would also round down to 18, and you therefore wouldn't see the difference. So it's what I call slicing the data too thin, right? We're trying to see too much data within too short of a period of time to appreciate enough of a change to properly determine if it's in fact following trend. So this is a quick graphical representation just to show you that at sample number 3, those two data lines are perfectly following each other. But the blue line is if it continues on a normal trend. The orange line is if it starts to continue on an abnormal trend. And as you can see, if you wait till sample number 4, the difference between those two lines is significant and you can see it. But the closer you get, the more times you sample between sample 4 and sample 3, the harder and harder it will be to see the difference. So I encourage people, pick an interval, stick to the interval. Don't shift it around. The more consistent you can be on the interval, the more normalized your data can appear and the easier it is for you to see when it's not normal. Now, of course, the first question most people have is, well, what should that interval be? Well, this is an example of the Goldilocks principle. This is related to vibration analysis, not oil analysis, but it is a study that was done by Chevron, and they were taking vibration readings every other month. And in doing so, they caught about 2/3 of the problems they thought vibration analysis should catch, which they didn't think was high enough. So they cut the interval in half, and they started taking vibration readings every month. And they got about a 30% increase in the number of faults that the vibration was detecting. They thought this was fantastic. So they decided to cut the interval in half again and start taking readings twice a month. And they got a 2% increase. So there's such a thing on the left as not often enough, and such a thing on the right as too often. But in the middle we have, as Goldilocks said, just right. So ultimately, we're going for what feels like just right. We need to come up with an interval that we don't miss too many problems, but we're also not oversampling and not getting a return on that investment. So as guidance, you could refer to something like the Basic Handbook of Lubrication, which lists this chart. And as you can see, the top half is engines, the bottom half is industrial equipment. The common denominator for engines is generally they're sampled at drain. And the common denominator for industrial equipment is it's generally sampled monthly or quarterly. Well, one of the other standards that exists out there is the STM D6224, which is the standard guide for in-service condition monitoring of auxiliary power plant equipment. But people often use this in a lot of other industries. And that very top row lists the suggested frequency, which again, you can see basically boils down to quarterly for everything other than engines. Engines down here at the bottom says every 250 to 500 hours, which tends to be oil drain intervals. So both those published documents are more or less in agreement with each other, but that still doesn't really answer the question. So I always say consider those kind of guidelines as a starting point. Where you set your interval is going to depend on some other outside factors. What's the load, the environment, the temperature, and the speed? If those are at extremes, probably going to sample more frequently than that guideline. If there tends to be high cost due to downtime, parts, labor, whatever it might be, you might sample a bit more frequently. If there's a safety requirement, well, you're going to have to at least meet that requirement. If the equipment is not very tolerant, then you might sample a little bit more frequently. And if you know there's high levels of contamination near it, again, you probably included that in the environment statement. But if there's some other form of contamination that's maybe more or less internal, then again, you may decide to sample a bit more frequently. So ultimately, it comes down to sort of a decision tree, if you will. And this is the one that I've created that I use. And I assume, without knowing anything, that everything should be sampled quarterly. Now, whether I decide to go more or less often depends on essentially at least these 4 questions. So if it's critical, I might sample it more frequently. If it's not critical, I might actually sample it less frequently. If it's expensive to repair, again, I shift towards more frequently. And if it's not very expensive, it's an off-the-shelf part, can be changed out in half an hour, I might go less frequently. If it's a condition-based oil change is one of your primary goals, your oil analysis program, I will adjust my thinking so that I get at least 3 to 6 data points. And what I mean by this is if one of your primary reasons for taking an oil sample is to determine when to change the oil, but it's a critical piece of equipment that's expensive to repair, you might have landed on monthly sampling from those questions. But you don't need, if as an example, the oil is going to last 5 years, you don't need to do monthly sampling for 5 years simply to determine the oil change interval, right? 60 points of data is a bit much. So you can probably back that off to semi-annual if that's all you're looking for. And the last question that has a significant effect is if it's a large volume. And if we have a large volume, I mean over 4 drums of oil going in there, you tend to dilute a lot of the things that are changing, the acid numbers, particle counts, water content, etc. And it's not that logical to take necessarily monthly samples on a 3,000 gallon system. It's not likely to shift by much from month to month. You need to stretch out your intervals so the change becomes a bit more obvious. So just to kind of wrap up here and give you 2 quick examples. If it's a critical, expensive to repair machine and you have a condition-based drain interval, you still might land on monthly because you might decide the criticality and the expenses that are involved just simply dictate you don't want any other issues coming up. But if it happens to be a large volume, you may be able to back that off to quarterly. The other example, though, is if it's not critical, it's inexpensive, you change the oil once a year, whether it needs it or not, well, then the logic may be you simply don't sample it at all. That it's not necessarily worth spending any of your condition monitoring budget to go over that way, particularly if it happens to be a fairly reliable piece of equipment that reaches its oil drain intervals without any other issues. So it kind of gives you two quick examples to consider in terms of how to use that flow chart. So in summary, I'll let Carrie wrap us up here. All right, I'll wrap us up. So we need to take good samples. Without good samples, we don't get good data. Without good data, our program has probably already failed. We need to consider the tools to take the samples. So if we sample with decent hardware from a decent location, well then we're already getting ourselves closer to having normal data that can, of course, lead to a good program. The procedures, as I said, they do not have to be complicated. In fact, the simpler the better, but understand simply done is also simply or easy to do a mistake or make some misjudgment along there. So ultimately what we're trying to go for is consistency. So even if it's not exactly the best procedure, but it's one that can be done consistently, that will give us, again, normal data. And last but not least, the frequency has to be, like the Goldilocks principle, often enough. We need to decide that we're catching problems at a pace that is giving us good return on our investment, that sampling any more frequently is likely to be a waste of time and effort. But if we do have something that has failed that we felt oil analysis should have caught, then we will sample that particular machine a bit more frequently. We don't necessarily need to adjust every other machine within our program. So with that, I will now turn it over to any questions. If you want to ask questions during the webinar, or of course, you can always send me an email after the fact, and I will get back to you.
Evan,
Carrie, have there been any questions?
I am here now. Sorry. Thank you for wrapping up for me. We had some questions during the webinar that I went ahead and handled. If anybody has any additional questions, please do send an email to Evan and he will answer those for you. It looks like we're right at our ending time, so I'm just going to go ahead and wrap us up and say, don't forget to download the handout real quick. I'll leave the webinar on for just a minute when we wrap up, but just click on the download button. That's a great ebook that kind of goes over a lot of what Evan talked about, and then you will get an automated email that will have some survey questions. If you please would answer those, it really helps us know what we're doing good and what we need to improve. And then I'll also send an email in about an hour or so with a link to the recording of this webinar, as well as a PDF of the slide deck. So thank you again, everybody, for attending. I hope you enjoyed the webinar. I always love to hear this one. I think it's a lot of really great information. Our customers always ask about sampling best practices. So this is always one of our most well-attended webinars we have. So thanks, Evan, and everyone have a great day.
All right, thank you.